Greetings, dear YouTuber viewers. My name is Yonadav. Hello, I'm from Israel, and I'm happy to announce that from now on I'm going to explain my experiments in English, so you, the viewers, can understand a little bit better, and I want to educate you about my findings on certain Bedini-Tesla effects. And this is first lesson. I don't know how many lessons I'm going to do. I'm also a student of the experiment, so don't think of me as some kind of someone who understands this phenomena. First thing I want to talk about, I want to talk about a certain formula. There has been some people who argued with me about certain things in electricity, so I want to make all of that clear. So I want us to explore the basic rules of electricity. So the most simple and elegant formula is Ohm's law, which basically means this. Okay, I'm not going to explain what this means, so if you don't understand, you can look for it on the internet. Now, let's see, this is current, and current is usually measured by ampere units. So what is an ampere? Well, an ampere is a certain number, a very big number of electrons per second. Coulomb per second. This very big number of electrons is called Coulomb. Okay, so the ampere is a Coulomb per second. For those that didn't understand, all of these formulas have a measure of time inside of them. If you don't have time, you don't have nothing. We can also see it if we go to the web or any place where you got formulas for electricity. Here you go. And you can see here's the ampere. Unit time, numbers of electrons per second. Okay? So I'm not making this up. Another formula we are going to talk about is this formula. this formula is about current, which is measured by ampere, and electric charge per unit of time. So, what is charge? Electric charge. Electric charge can be explained by this formula, which basically means having a certain amount of current per time, which can give you charge. I'm interested in this formula because in here what we want to talk about is some kind of a capacitor or a battery. So a battery's charge can be considered as the amount of current that battery can output for a certain amount of time. Okay, so if you have a 12-volt battery with a 3.2 ampere hour, this means that our battery has 12 volts and it can put out 3.2 amperes, which is measured in time, for 1 hour. So this is basically a charge, and this is voltage. Without voltage we will also have no power, because the voltage is the potential. Without the potential, the current won't flow. So if we want to know the amount of energy we have in a certain cell, let's call it a cell, a battery or a capacitor, we just multiply the voltage in the charge. Okay, this is the charge. Could add to ampere for this, which is 1 hour. Okay, and this will give us a certain amount of power. Now that power is not just a number. If we had no time, then we would have 0 in here. Since we've got time, we are talking about something which is real. It's not just a number. It can be considered as a force. Now, this P can present joules, or it can present watts per second. Why per second? Well, this formula makes it very clear. If we have a certain amount of watts, which is worth our charge, this time we're talking about current, which is measured by ampere, which is a coulomb per second. So we have time in this formula. We have a second here per voltage. So if you just multiply these two, you have a number per second. So the number of watts will be per second. Okay. That's just to show you how you should treat this formula, okay? So in this formula we also have a certain number per second. It's not just a number, it's a measure of energy. This is a measure of energy, and this is also a measure of energy. So let's see. You see? It's very simple. Very simple. A charge is just a bigger number, so this will be bigger too, and it will be measured in joules or watts per second. Okay, so that's very simple. Now let's introduce you to a certain effect. If we have, let's say, a standing voltage, we are not interested in the integrals or differentials or stuff like that. We want this to be very simple so everyone can understand. So the voltage is constant in this battery, let's say 12 volts. Okay, and we have a certain charge, which is Q. Q can be, I don't know, 3 ampere per hour. Okay, we can measure how many watts per second we can get out of this for 1 second. This will be the amount of watts per second. Very simple. That's how we know how much energy we have in this cell. So, according to this formula, we don't have to treat this as current. We can just treat it as charge. Okay? It doesn't, charge is not a measurement of current. It's a measurement that equals current per a certain amount of time. It means that if I have a battery with a certain charge, I can pull a certain amount of current for a certain amount of time. But I don't have to do that. That charge can just stay still. And so the voltage will also stay still. So this formula doesn't necessarily contain current at all in it. This is static. That's why this is sort of a static electricity inside the capacitor, inside the battery. It's static, it's just there. Okay? We will have current involved when we will have a certain circuit, and current will start flowing. Then, because we know the charge, we know for how long we can sustain that certain amount of current. Okay? So, according to this formula, which I did not invent, the amount of power or energy inside the cell is measured by both charge and voltage. So if this battery will have a higher voltage, you'll have a higher potential for work. And if the charge will be bigger, then of course this also applies. So what happens if for a certain amount of time I produce a very high voltage, higher than 12 volts? There is a time to this certain voltage. Now, if you want to do this with current, then all you have to do is put here a higher voltage, let's say 20 volts. Okay, and now the differential will be 8 volts. You see? And the current will be decided by the difference in potential and resistance. Okay? So if we have 8 ohms, which is a measurement of electric resistance, and we have a potential from this to this, from this point to this point, of 8 volts, so we will have a flow of 1 ampere. In this case, this cell is not exposed to a higher voltage, it's just exposed to current. Okay? And since it's exposed to current, the voltage and charge of this cell will start to increase. The charge will start increasing, and as a result, the voltage will also rise. It's like an indicator. But what happens if I produce inside the battery a higher voltage for a very short amount of time? For that certain amount of time, if I had 12 volts, now suddenly I have 50 volts. we can see what happens to the amount of energy we have in the battery. This also applies in this conditional condition, when I just put a certain amount of current for a certain amount of time. You see? So I'm getting a higher charge. Simple. I'm just enlarging my charge. In here, I'm enlarging the voltage, which is different. If I'm only enlarging the voltage, that means I'm not using current. Okay, now if I use current, voltage will rise. Okay, now think of this as a very stable battery, so voltage doesn't rise a lot, but it does rise. But what happens if I make this battery go higher in voltage without using current at all? What happens? Well, according to the numbers, power will rise. Of course, when you measure it on time, the amount of energy will not rise that much, because think about it. We have a certain amount of time where voltage is still, then we have a glitch like this and keeps going, something like that. Now you can see that there's a certain step in voltage. That's an indicator that the charge grew without current. Okay, so what actually happened? For a certain amount of time, the voltage was still, so the difference in voltage was 0, and so the energy contained in the cell stayed the same. Now, when voltage goes up, again for a certain amount of time, so this is not just a formula of numbers, there is also time involved. You see? Since there's time, the voltage rises and then back it down, but it didn't come back to normal. And why is that? Because for that small amount of time, for that window of time, we had a higher voltage. And what happens when we have a higher voltage? Voltage determines the direction of current, of the magnetic field. And so what happens inside the battery is that the electrons and the ions will just go backwards. So the battery will charge itself, which is also a term I did not invent. So if you can produce an effect like that, everything will move according to voltage. So the charge will grow by itself, and that's why you'll have a certain amount, you'll have a little step. Okay? And this is what Bedini does, and what Tesla does. they're using this formula to increase voltage but not current. And when they do that, they can gain power without losing their voltage, because if their source that creates the effect is using a very little current to create a very high voltage, then the charging cell will receive all that power, but the power source will not be as depleted because you don't use current. And as we can see by the formula of charge, the charge will be determined by the amount of current you can pull out for a certain amount of time. So if I create a high voltage for a very low amount of current, low current, high voltage, my charge will not deplete as much. And that's what we're doing here. And the battery will charge itself. I'm sorry, this is presented in this fashion, not very ordered, like I'll try to get better at explaining this stuff to you, and explaining the effects of radiant energy, which is why I'm doing these videos. So please stay tuned and comment and ask questions, because this is important stuff. And what we are interested is in the effect of producing very high voltage with very little amount of current. Okay, so until lesson 2 comes, that's it for now.